Okay, welcome back. So, at the end of the last video, we talked about putting the electrons in the lowest energy shell, which translates to putting it into the lowest energy subshell, which means the lowest energy orbital. And so you fill the 1s orbital first, then you fill the 2s first, and then when it comes to oxygen, you fill the electrons, one electron in each orbital in the p subshell, first of all, and then the last electron is paired up. When you pair up your electrons, there is a repulsion between these electrons. And that's a really important point when we come to look at ionization energy later on. It says here, this explains why it's easier to remove an electron from an oxygen atom than a nitrogen atom. So, okay, we get to fluorine. Fluorine follows the same rules. Okay, we just put in the fifth electron of the p subshell into this second orbital here, and then similarly when we get to neon, we've now filled our p subshell, and our electron configuration is written as 1s2, 2s2, 2p6, where the big number represents the energy level, the letter represents the subshell, and the superscript number represents the number of electrons in each subshell. Okay. Okay. So, for sodium to argon, we follow the same rules, and so we find that we put the next electron in the 3s subshell. The one after that also goes into the 3s subshell because that is lower in energy than the 3p subshell. Even though there is this repulsion between these electrons, that is insignificant relative to the energy hike here, going to a new subshell. So then argon will have this electron configuration: 1s2, 2s2, 2p6, 3s2, 3p6. If you want, pause the video, work out and see the logic behind these different electron configurations here. Okay. Okay, now for potassium, its highest energy electron actually goes in the 4s subshell. It doesn't go in the 3d, because we said on the last video that the 4s subshell is lower in energy than the 3d. So, so that electron for potassium, the 19th electron of potassium, goes into the 4s subshell. For calcium, the 20th electron goes into the 4s subshell, and it is paired up. Okay. Now, something that you may not have appreciated at this point, if I can just find, okay, if I can just move this. Okay, looking at the periodic table. Okay, have you ever wondered why the periodic table has two columns here, 10 columns here, 6 columns here? Okay, if I was to tell you that these two columns are called the S block, these 5 columns here are called the D block, and these 6 columns are called the P block. Hopefully by now, by process of elimination, you've worked out that these are called the F block. Okay, and the reason for that is because the highest energy electron for sodium or rubidium or strontium will be in an S orbital or an S subshell. Likewise, the highest energy electron in, say, aluminium or antimony or bromine or radon, it is in a P orbital or a P subshell. And so hopefully you see the point now that for like zirconium, manganese, iridium, copper, the highest energy electron will be in a D orbital or a D subshell. Okay. So, what this is saying here, let me just expand it back up. So all this says here, all elements with a 1s electron configuration will be in group 1. All elements with an S2 electron configuration will be in group 2. Okay, and so these are known as the S block elements. And if we just go back the slide, then you can see here that sodium 3s1, magnesium 3s2, and if we were to go back a little bit further, beryllium, that's in group 2, lithium, that's in group 1. Okay. Oh, sorry, got too far now. Okay. So when it comes to the d orbitals, okay, so scandium. Scandium puts the first 20 electrons in the orbitals as calcium did, and now its 21st electron has to go in the lowest available energy level. It is the 3D, the lowest available energy subshell, so it is the 3D subshell, and we put the electron in just this vacant 3D orbital. Okay. When it comes to titanium, it's the Hund's rule, maximum multiplicity. Okay, or the sitting on the bus rule. Okay, one person sat on a seat, 4 empty seats. You go and put yourself on an empty seat. Okay, so you will see that for the next one, which is vanadium. Now, chromium. Well, what? Chromium is the 4th element in the D block. Now, you would have expected that chromium to have four electrons in the D block, sorry, in these D orbitals. But we've got 5. Where's the 5th one come from? Okay, the 5th one has come from this 4s orbital here. And the reason for this is that it's actually just a lower energy configuration to have one electron in an S subshell and the 5 electrons in the 5 different orbitals in the D block. Okay, so what we've done here is that we have minimized the repulsion between these 2 electrons, and what this schematic doesn't show is just how similar these energy levels are, these orbitals are in energy. So, so that's why that happens. Okay, so when it comes to the next element, which is manganese, manganese goes back to having the expected electron configuration of 4s2 3d5. Okay, so chromium is one exception. If we keep going along, we keep putting our electrons, pairing them up, and then we get to copper. And copper, again, instead of having 9 electrons in the d subshells, sorry, in the d orbitals, we put 1 electron into the 3d orbital to make it an electron configuration of 4s1, 3d10. And again, this just happens to be a lower energy arrangement than having it 4s2, 3d9. Okay, you don't need to explain it. You just need to be able to remember it. And then zinc has 4s2, 3d10. Okay. The remaining remaining orbitals in the 4p subshell, okay, these will be filled up as such from gallium to krypton, and so you have these. So gallium will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Okay, sorry, that's a typo. Germanium should be 4p2. Now, as you can see, it's a bit of a faff trying to write all of this out. And what we can use is the shortened form, which is using the form, we use the chemical symbol of the previous noble gas. So argon has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. So if we write Ar in square brackets, then the reader knows that that means 1s2, 2s2, 2p6, 3s2, 3p6. And then you can just concentrate on the higher energy electrons, which are 4s2, 3d10, 4p3 for arsenic. So, okay. And here's just a nice little summary of the first 30 elements. Okay, so just very briefly, electron configuration of ions. If you got a positive ion, you remove 1 electron from the highest energy orbital. So in this case, sodium has a sodium atom has the electron configuration 1s2, 2s2, 2p6, 3s1. The sodium ion, it's lost its highest energy electron, and it has this electron configuration 1s2, 2s2, 2p6. Coincidentally, that is the same electron configuration as a neon atom. And so we say that these two species, the sodium ion and a neon atom, are isoelectronic. If you're making a negative ion, you add an electron to the highest energy orbital. So for example, chlorine got the electron configuration 1s2, 2s2, 2p6, 3s2, 3p5. A chloride ion, negative charge, is gained 1 electron, goes up to 3s2, 3p6. Okay. And the curious thing about the first row of transition metals is that, it just gets complicated, is that the 4s electrons are removed before the 3d electrons. And that goes for all of the transition elements that we have, all the d block elements. So you can see that titanium, 4s2, 3d2 electron configuration, and then these are the other configurations. Okay, time's run out. Thanks for watching.